Every day, your phone recognizes faces, your watch tracks your steps, and your favorite app suggests what you might like next. Have you ever wondered how all this works? It might seem like magic, but behind the scenes, there's a powerful mathematical tool at work: calculus. Calculus helps computers and apps understand change, like how your activity level varies throughout the day, or how your preferences shift over time. Imagine a streaming service. It learns what you enjoy by tracking how your interests change, using calculus to adjust its recommendations as you watch more shows. Or think about facial recognition. Calculus helps algorithms spot tiny changes in images, so your phone can unlock with just a glance. You might remember calculus as a tough subject in school, but at its heart, it's a way to describe and predict how things change, step by step. In machine learning, calculus is the secret engine. It helps algorithms learn from data, improve with feedback, and make smarter decisions. Think of a machine learning model as a student. At first it makes mistakes. Calculus gives it feedback, showing how far off it is and how to adjust. With each step, calculus guides the model to reduce its errors, getting better and better at its task, just like a student learning from mistakes. So, the next time your device surprises you with a perfect suggestion, remember, it's not magic, it's calculus, quietly powering the smart technology all around us. Calculus is often called the science of change. But what does that really mean? Let's break it down together. Before we dive in, let's compare calculus to something you already know: algebra. Algebra is about finding unknown numbers, like solving for x in an equation. For example, if a teacher writes 2 plus 3 and 7 on the board, you figure out that x equals 2. Algebra helps us answer, what number makes this equation true? But what if things are changing? Imagine a car speeding up, the temperature rising, or the number of app users growing every minute. These are all examples of change in action. Calculus is the mathematics that lets us describe and analyze these changes. It helps us answer questions like, how fast is the car moving right now? Or, when is the app growing the fastest? Nothing in the real world is truly static. Everything is in motion, always changing, sometimes slowly, sometimes rapidly. Calculus gives us the tools to study these dynamic processes with incredible precision. It lets us zoom in and see exactly how things are changing at any moment. Calculus is generally split into two main branches. First, differential calculus. Think of it as using a super-powered microscope to find the exact rate of change at a single instant. The second branch is integral calculus. Imagine adding up tiny pieces to find the whole, like measuring the area under a curve, or the total distance traveled. Together, these two branches let us understand and predict the world in motion. From physics to finance, biology to machine learning. Let's explore one of the most powerful ideas in calculus, the derivative. Imagine you're standing on a hill, looking at the landscape. The steepness beneath your feet is the slope at that exact spot. In simple terms, the derivative tells you how steep a graph is at a single point, just like the angle of the hill where you stand. For a straight road, the slope never changes. It's always the same. You can pick any 2 points and measure the rise over the run. But real life is full of hills and valleys. A gentle hill has a small slope. A steep cliff has a large slope. Slope is the rate of change, how quickly you rise or fall. Now, imagine a roller coaster. The track curves up and down, twisting through gentle slopes, steep climbs, and sharp drops. The slope is always changing. To find the slope at a single point on a curve, we zoom in, so close that the curve looks almost straight. The derivative is the slope of this tiny, just touching line called the tangent. If the tangent slopes upward, the derivative is positive, the function is rising. If it slopes downward, the derivative is negative, the function is falling. If it's flat, the derivative is zero, like a hilltop or valley bottom. In machine learning, we use derivatives to understand how our error changes as we adjust the model. Imagine the error as a landscape of hills and valleys. The derivative tells us which way is downhill. For example, on a distance time graph, the derivative at any instant is your speed right now, just like a speedometer in a car. In business, if you plot profit versus ad spend, the derivative tells you the marginal return right now. A high slope means more profit per dollar. A flat slope means diminishing returns. So far, we've looked at functions with just one input. But in real-world machine learning, models often depend on many variables at once, like ingredients in a recipe. Imagine you're baking a cake. The taste depends on flour, sugar, eggs, and butter. If you change just the sugar, keeping everything else the same, you can see how sweetness changes. In the same way, a house price model might use bedrooms, square footage, age, and neighborhood quality. The error, the difference between predicted and actual price, depends on all these variables. A partial derivative measures how the outcome changes if you adjust just one variable, like tweaking only the sugar in your cake, while keeping all others fixed. In math, we treat all other variables as constants, wiggle just one, and see how the result shifts. This is the essence of a partial derivative. For example, the partial derivative with respect to bedrooms tells us how the error changes if we tweak just the bedroom's weight, keeping all other features the same. We repeat this process for every variable: sugar, flour, eggs, or in our model, bedrooms, square footage, and so on, to get a set of partial derivatives. Stack all these partials together, and you get a vector called the gradient. The gradient points in the direction where the function increases fastest. Picture standing on a hilly landscape in thick fog. The gradient is like a magical arrow showing you which way is uphill. But in machine learning, we want to minimize error, so we walk in the opposite direction, downhill, following the negative gradient. This is how models learn, by taking small steps in the direction that reduces error the fastest, guided by the gradient at every point. In summary, partial derivatives let us see how each variable affects the outcome, and the gradient combines them to guide us toward the best solution. In machine learning, optimization is like searching for the best answer in a sea of possibilities. Imagine you want to draw the perfect line through a cloud of data points. Your goal is to make predictions as accurate as possible. To measure how well our line fits, we use a loss function. The most common is the sum of squared errors, or SSE. For each point, we look at the vertical distance from the point to the line, square it, and add them all up. The lower the total error, the better our line. But how do we find the line with the smallest error? This is where calculus comes in. Imagine the error for every possible line as a landscape, a smooth bowl. The bottom of the bowl is the best fit, where error is smallest. Instead of guessing, we use derivatives to find the direction of steepest descent. The gradient points uphill, so we step in the opposite direction, downhill, toward less error. This process is called gradient descent. At each step, we recalculate the gradient and take another step, gradually approaching the minimum error. As we get closer to the bottom, our steps shrink, and the line we fit to the data becomes more accurate. This is how machines learn the best solution, one careful step at a time. Whether predicting test scores, house prices, or recognizing images, optimization and calculus work together to help machines find the best answers from data. Imagine you're standing at the top of a hill, surrounded by fog. Your goal is to reach the lowest point in the valley, but you can't see very far ahead. This is what gradient descent does for machine learning models. It helps them find the lowest point, the best solution, by taking small, careful steps. At each step, the model checks which direction is steepest, like feeling which way the ground slopes under your feet. It then takes a small step downhill, moving closer to the valley floor. This step is guided by the gradient, the mathematical direction of steepest descent. After each move, the model checks again. Am I at the lowest point yet? If not, it repeats the process. Step, check, step, check. The size of each step is called the learning rate. If the steps are too small, it takes forever to reach the bottom. If they're too big, you might overshoot and bounce around, never settling down. It's like tuning a radio. Turn the dial too quickly and you miss the station. Too slowly and it takes ages to find the right spot. As the model gets closer to the bottom, the slope flattens out. The steps become smaller, and eventually the model settles at the lowest point, the best answer it can find. This process works for simple models, like drawing a straight line through data, and for complex ones, like training deep neural networks. Gradient descent is the step-by-step engine that lets machines learn from data, one careful move at a time. As we reach the end of our journey, let's reflect on the true power of calculus in the world of machine learning. Calculus isn't just abstract trivia, it's the vibrant, beating heart that powers modern technology, from facial recognition to personalized recommendations. The derivative measures instantaneous change, the slope at a single point, even when dealing with millions of variables. By understanding slope, we can navigate vast search spaces, finding the best solutions in a sea of possibilities. We define a loss, visualize an error landscape, and seek the lowest valley, where our model performs best. The gradient, a vector of partial derivatives, points us uphill, but we step in the opposite direction, walking downhill toward minimum error. This is how machines learn, not by magic, but through beautiful practical mathematics in action. Calculus gives us the language of feedback and the mechanism for improvement, showing what to change, and by how much. Remember, the slope at a point, the derivative, and the gradient pointing the way downhill. With these, we optimize, adapt, and make machines smarter. From movie recommendations to medical breakthroughs, calculus turns raw data into intelligence, the secret engine that makes data science truly smart.